Let's continue on now with the second part of our discussion about how concurrent programs are developed in Java. And this is going to focus on the interaction mechanisms in a bit more detail. So the shared objects / synchronizers and message passing. So Java threads interact using shared objects and or message passing if they're written well, if they're well designed. And shared objects are typically used to synchronize concurrent operations to ensure certain properties. Most commonly mutual exclusion, but there's other things you can do with them as well, as we'll see. And one of the key themes in shared objects is this concept of a critical section. So what you typically have is you have some kind of object, such as a message queue or something else, and you have multiple threads that are trying to access this object's state to either read and or write to it. And in order to keep things from getting corrupted and having problems with things like race conditions or visibility challenges, you have some kind of synchronizer, some kind of lock, typically a Java reentrant lock or an intrinsic lock. And when the threads come along here, the first thread to arrive acquires the lock, and then it can operate in the critical section. It can read and write to the state of that object securely, not having to worry about corruption and so on. Any other threads that come along while the lock is held have to wait. And then when the first thread is done with whatever it's doing, it releases the lock, exits the critical section, and then another thread will be allowed to come in. And there's a whole bunch of stuff about contention and thread ordering and the notification model, blah, 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 which we will not go into in detail in this class, but it's interesting, and it involves the use of shared objects. Here are some of the key types of synchronizers you can have. One are the properties that are supported, one of which is atomicity. Atomicity ensures an action either happens completely or doesn't happen at all. Lots of great examples of this from the world of science fiction and science fantasy. If you're a Star Trek fan, the transporter beam is an example of atomicity. You do not want to beam someone partly from one place to another. That would be bad. If you're a Harry Potter fan, the concept of splinching or apparition or disapparition, I can never remember why it's apparition and disapparition, but in any case, transporting yourself from one place to another, you do not want to do that non-atomically. That's called splinching. You leave your nose behind and stuff like that. So that's all about atomicity. There's a bunch of features that enable that. Mutual exclusion, we just talked about that in the context of critical sections. It ensures that interactions between threads will not corrupt shared mutable data or shared mutable state. So we don't want them the threads crashing into each other. Always think about the protocol for using the restroom in an airplane as an example of mutual exclusion and the way that that protocol works. Coordination is also another type of synchronization mechanism, which ensures that operations between multiple threads occur in the right order, at the right time, and or under the right conditions. And one of the key themes there is conditions. When can something happen? So for example, if you've got multiple threads that are trying to coordinate through a bounded buffer, some kind of synchronized message queue or thread-safe message queue, you want to make sure that you coordinate the activities so when a thread comes to retrieve an element from the queue that's shared, if there's nothing in there, it's going to have to wait until the condition reaches what it needs, which is there's something in the queue. Likewise, if a thread comes along and wants to put something into a queue and the queue is full, it likewise has to wait for the condition to be not full. And then the other type of property you might want to have are ensuring that groups of threads wait for each other to reach a common execution point before they can continue on. So a classic example would be a starting gate at a horse race or starting blocks from a race like the Olympic 100-meter dash. You wouldn't want people to just show up randomly at the starting blocks of a race and just start running as soon as they show up. That probably wouldn't work very well, wouldn't be fair competition. There's also things, those are called entry barriers. There's also exit barriers where you wait until a bunch of threads have reached a finalization point or a completion point before letting them go on and do something else or before doing something else. There's a whole slew of Java synchronizers, including atomic operations and the volatile keyword. There's synchronized statements and methods. There's reentrant locks, readers-writers locks, stamp locks. There's semaphores, condition objects, barriers, and so on. These are all the types of things that occur in Java concurrent programs to keep them from scrambling things and ensure that corruption doesn't occur and making sure things occur at the right time in the right order under the right conditions. We're going to talk about almost none of this. So if you're interested in learning more about this, which you should be if you want to learn about concurrent programming, take a look at this particular playlist, which has hundreds of videos that talk about these topics in great detail. The reason why we're not going to talk about this stuff in this class is because parallel functional programs often have little or no need for synchronizers due to various things. One is they often work on so-called immutable data. Immutable data is data that does not change its value once it's initially set or created. And once something's immutable, there's no need to lock it because it's not going to change. There's also this concept you'll see a lot in parallel functional programming, which we'll start talking about shortly, about statelessness. In general, you want to make sure the behaviors you apply in a functional program, especially a parallel functional program, doesn't keep a history of what's happening. It can run in any order and requires no state or no knowledge of prior activities. And then the other thing that's really important, which we'll talk quite a bit about when we get into things like parallel streams, is the idea of data partitioning. You take a big source of data, like an array or a hash table or whatnot, and rather than having coordination required to ensure that the elements in that data structure are not corrupted by multiple threads trying to read or write to them simultaneously, instead you partition everything so that there is in fact no sharing. So one thread will deal with one portion of the data, another thread will run in parallel dealing with a different portion of the data, and so you split things up in a way where there is no need for sharing and no need for synchronization. So those are some of the ways in which we are not going to have to worry about this stuff because we're doing parallel programming, parallel functional programming, not concurrent programming. The other approach for coordination and interaction is message passing, where you have producers and consumers, and the producers generate data and put it into some kind of shared, thread-safe, synchronized buffer, message queue, blocking queue, whatnot, and then one or more threads take stuff out of that queue. And it typically is done with a so-called blocking queue, which means when the queue is empty, you have to wait for it to be not empty to get something out of it. And when the queue is full, you have to wait for the queue to be not full before you can put anything into it. This decouples the producers and consumers and enhances various quality attributes. For example, you can enhance scalability by having multiple consumers allocated so that you can scale things up. So that each one might run on a separate core. You can add more processing. It's like adding more people at a holiday season to Walmart so you can have more things processed and make the queues shorter. There's also the concept of flexibility. You can, by decoupling things, you can plug and play a different implementation of a supplier and a consumer without the other side really knowing what's happening. Load balancing is also enabled. You can have, in much the same way as scalability, you can have different numbers of consumers out there handling the work, and you can balance the load and try to keep them all busy and not have one queue build up. Failure isolation, if something goes wrong with one of the consumers, you might have a spare that you can bring in very quickly to take over and replicate things. And then, of course, reuse. You can reuse the elements without having tight coupling between the producers and consumers. There's a lot of Java thread-safe queues that can be used for message passing. The most common ones are the array blocking queue and the linked blocking queue. In my other class, we talk a lot more about these. There's a priority blocking queue, which just orders the incoming messages in priority order. There's something called a synchronous queue, which is used by cache thread pools. We're not going to talk much about that. And then there's also a very interesting data structure, which we will mention briefly later, called a concurrent linked queue. And the main difference between concurrent linked queue and these other queues is with a concurrent linked queue, all it does is make sure that adding and removing elements to or from the queue, respectively, will not corrupt the state. But there's no blocking. If the queue is empty, it doesn't block. If the queue is full, it doesn't block. It just basically makes sure that you can add or remove items from the queue concurrently without having to worry about race conditions. So that's the end of how concurrent programs are developed in Java. So at this point, you know a fair amount of what's going on conceptually for these features.